Okay. First, I would like to thank all of you and thank the conference organizers for inviting me to speak in this very well-respected conference. The topic that I'm going to cover today is related to the active suspension systems of cars. The title is Control of Active Suspension System Parameters and its Impact on Ride Comfort. This is a joint work with my colleagues, Dr. Fadli Darsifan and Dr. Farid Hasbullah. The outline of this talk, we will make a bit of an introduction, and then after this, what is the research for this research, and we'll talk about the nonlinear full car model, and then the control strategy ADRC, and also modified ADRC, which is ADRC IDD, and then result and conclusion. One of the important things that people are moving now, the international direction in vehicles in general, people are moving into more automated systems and at the same time also more intelligent systems. The future of automotive engineering, like also the future of aerospace engineering, is going to change drastically in the coming 10 to 15 years. And part of these changes is the implementation of intelligent subsystems, both in ground vehicles and also air vehicles and sea vehicles as well. Suspension system is one of the essential part of any car, because it is the way or the subsystem that will help having a kind of a ride comfort for the passenger. And usually the main two criteria that will be of interest to any buyer of any car is ride comfort and also ride handling, the handling of the car. Unfortunately, in any design of subsystems of a car, the ride comfort and also car handling are not really working hand in hand. So if you improve the car handling pretty much, the ride comfort will be a little bit problematic. If you improve the ride comfort too much, also the car handling will be a bit problematic. So usually in any design of cars, we have to compromise between ride comfort and car handling. And one of the ways that people are moving to is the active suspension, or sometimes called the intelligent suspension systems, that might have a better compromise between the ride comfort and also the car handling more than the passive suspension system. We are going to check four main criteria or three main criteria, in fact, for this, because when we talk about ride comfort, we talk about the acceleration, different types of acceleration according to the body movement of the car, heave, pitch, and roll. Mainly, many people will focus on heave only, but heave only, yes, it is one of the major measures, but in fact, pitch and roll also are quite important as well. And then from design point of view, from suspension design point of view, we need to look into the suspension deflection, because the deflection is restricted by the space available in the car design. So we need to look into this as well. And finally, to have a good grip on the road, which will represent the car handling, we need to have, or we need to measure the tire deflection. We need to measure the tire deflection. Here is a bit of some of the papers, the key papers. Actually, there are many, and the original paper have a lot of these papers. These are some of the key papers related to the active suspension. Some people have done it. The majority of the papers published before this paper is actually focusing more on the vertical acceleration, and some of them will add the pitch and roll acceleration. Not many will measure the suspension deflection or will measure the tire deflection. So this is why we moved into this direction, to have a better understanding. Many control systems has been used and in the suspension system, in active suspension system, and still people are using many of them. The problem is some of them are already implemented and some of them are under experimentation, and people are trying to get to the best and at the same time the simplest type of control, because industry usually will look at a kind of easy control system. Yeah, we can complicate the control system, but at the end of the day, the implementation, the actual implementation of the control system might be problematic for industry. So this is why mainly the industry will look into one of the easy controllers. One of the very common controllers that was introduced early on the 2000s by a few scholars, Gao and Han and many others, is called Active Disturbance Rejection Control, which is the abbreviation is ADRC. This control has been attractive for many applications. It has a reasonable robustness, and at the same time also we don't need many sensors actually to implement this control. Many people apply this control to many applications. One of them is mainly aircrafts, and some people use it for electric motors, and some people use it also for robotic arms. But the use in vehicle is not many. This is why we were intrigued to try to introduce it to the active suspension system. So the objective of this work basically is number one is to derive a nonlinear vehicle ride model, which I will explain why we are interested in this, and then after this to develop an ADRC model, and we develop an ADRC model with input decoupling transformation, which is called ADRC IDT, and compare these two for the performance of the suspension system compared with the passive performance. And based on this, we'll evaluate the result as possible. Modeling of cars, actually there are two ways to model cars. One way is a detailed model, which people will use finite element. Of course, this is one of the most complete modeling, but at the same time, it has many drawbacks. One of the drawbacks, it will need a lot of computational facilities, and it will need also a lot of computational time, and it will need a good expertise, in fact, to look into the result, because if you are not expert in finite element, you don't understand the tricks behind meshing and selection of elements and many of these things, the result might be deceiving and might not be correct. The other way that people have been using commonly in vehicle dynamic is what we call discrete car models. Discrete car models have been used extensively in vehicle dynamic since early maybe 60s or 50s up to this moment. So people still, and the result out of this discrete models usually will give a good estimate of the dynamics of the system. Will give a good estimate of the dynamics of the system. And if we want to move to a further refinement, we can go for experimentation or we can go for finite element analysis. Mainly, most of the discrete systems that people implement are linear systems. So we raised the question to ourselves whether if we introduce nonlinearity, it will make a difference or not. So this was the first question in this research. And we can classify the different types of nonlinearity into geometric nonlinearity, which would be inherent to the geometry of the system, and then nonlinearity due to the suspension spring, and nonlinearity due to damper. So these are the three main types of nonlinearity that can be introduced into the discrete system. This is 7 degrees of freedom full car model. Of course, it's quite common. This is quite known in the literature, and we just added the nonlinear part in it. When we compared the result or the impact of nonlinearity between linear and nonlinear models for the discrete system, we found that in fact the linear solution is good enough up to a very high number of for example, input heights related if we have a kind of a pulse mode or anything like this. So the linear system will give us a very good result unless the height of the input is very, very high, which is usually is not common in paved roads. It's not common for passenger cars. It might be for military cars, yes, but for passenger cars, it's not that common. So basically, we concluded that the linear system will be good enough to evaluate what we need to evaluate. And these are the equations. I will not go through the details of these equations. So if anybody interested, I can send the paper to look at, and it's already published in a journal. Again, this is also a kind of comparison between the linear and nonlinear spring and linear and nonlinear damping. The most influential part is for the damping effect. And we discovered that damping, unless for a certain domain, the linear and the nonlinear damping will have a bit of a different result. But if we move for a very small domain, in general, domain of speed, then the linear damping will be good enough. For spring, the domain is much more higher. The linear domain is much more higher. The idea of ADRC, again, also I'll not go into much details because I know the time is not, but I'll just point out, and of course, there's a lot of information and papers about ADRC. We have an outer loop and inner loop, and the outer loop, which is the feedback controller, and the inner loop, which consists of extended state observer to estimate the total disturbance and a disturbance rejection scheme. So this how it is. The idea behind ADRC is that if the external disturbances and internal disturbances can be approximated in real time, then they can be cancelled out without having to know the accurate analytical model of these disturbances. And this is one of the key issues that made ADRC a bit attractive to many researchers, because it's a bit simpler in this aspect. So we don't need to evaluate or make a kind of accurate analytical model for the disturbances that might take place in the car. Also, the extended is designed to estimate the internal and external disturbances function, and this only requires input-output data of the plan. So we don't need to know the details of the plan. So this will simplify the things. This is how the idea behind ADRC and adding to it the decoupling. But I will just go quickly to the results. Okay. For the result now, we are comparing now between the typical speed hump profile. As I mentioned, we are talking about passenger cars. We are not talking about cars which are off-road vehicles. Off-road vehicles will have a different treatment. And as I mentioned also, the treatment might involve nonlinearity to a great extent, especially if we are talking about military applications and other things. But for passenger cars, this profile can be quite representative of the situation. This is most of the road profiles will have. So according to many publications and literature, the height will move between 0.076 to 0.09 meter, and the travel length of any hump also will move from 3.7 to 4.3. These are the common things that people will use for the hump profile. At the same time, also usually the speed of the car should not exceed around 40 kilometers per hour when you are passing through or over a hump. Otherwise, of course, this will be against the regulation of the traffic. This is a response to speed hump input. So we can see now the vertical acceleration the pitch acceleration, and we can see also the roll acceleration. All of them are plotted against time to see the transient part, and then how it will come to a kind of a stabilized situation. Definitely, as I mentioned before, we are comparing between ADRC and ADRC IDT and the passive suspension system. If we look carefully at, I hope it's a bit clear because it has some colors and other things. So if we look carefully, we will find that the best result in general will be ADRC with IDT together. We'll have a better result than ADRC. But also ADRC is not that far. It's not that far from the ADRC IDT. At the same time, of course, the comparison to the passive, we see that there is a lot of improvement. There's a lot of improvement. And as I mentioned, one of the key issues for ride quality is to look into the different accelerations of the car body, specifically the heave and pitch and roll. This is another also comparison. This is another way to compare the result. If we look at ADRC and ADRC IDT, we'll see the percentage of reduction based on the previous analysis. And we will find that ADRC IDT have a bigger advantage, definitely, in the performance, a bigger advantage in the performance. Now, of course, the classical way of evaluating the vehicle, the ride comfort, is using a hump or using a pulse, something similar to a pulse that a car will go through. And we need also to compare with a road profile which is close to the real road profile. And the road profile in general will be represented in vehicle dynamics as a random excitation, will be represented as a random excitation. So this is one of the ways to represent. There's actually a lot of models for the road profile, and we selected this one following a couple of well-known scholars who have been using it for a while, and the result also, the result of their research is quite close to reality. Which are Kapustiak and also he and his group. When we use the random excitation, the road profile, the random excitation as a road profile, again, the result will be consistent that the ADRC IDT is giving a better result than the ADRC. And definitely, we didn't put here the passive because the passive will be no comparison to this one. But at the same time, also, if we look at the different different tires, if we look at the different tires, the first couple of figures, figure 18 and figure 20, will give a kind of an overall. But if we look at the different tires, we will discover that at the right front and also right rear, sometimes the ADRC alone will give a better result than the ADRC IDT. Our analysis, this can be for many possible things. Sometimes also it depends on the design of the car. It depends, this car is front drive or rear drive. So many things that actually we don't really consider much in the discrete model, but definitely we can consider it in a finite element model. So this issue might need further investigation to look carefully what is the reason behind it exactly. The conclusion is ADRC will give a better ride performance, high control effort. And we need 4 ADRC controllers, 1 for each actuator. ADRC, IDT, again, we'll have better trade-off, lower control effort, and we will need a lower number of controllers. lower number of controllers, 3 controllers. And again, this is one of the things that made ADRC and ADRC IDT quite of interest to many industrial application to this moment. By this, I think I covered my presentation, and I'll be happy if any of you have any comment, clarification, or question. Thank you very much.
Thank you, Dr. Waleed.
Thank you very much, Dr. Waleed, for interesting presentation. Any questions from all?
Yes, please. Hello, Dr. Waleed. I am Dr. Ahmed Farouk from Zagazig.
أهلا وسهلا يا دكتور أحمد. Welcome. Long time back. We didn't meet my good friend. How are you doing?
This is very nice to meet virtually after long years.
Yes, yes.
I'm really happy to meet you. I hope to meet you face to face soon, inshallah.
Inshallah, we hope, inshallah. After this lockdown, I think in Egypt there's not much lockdown, but outside there's a lot of lockdown. So hopefully this lockdown
Yes.
will be, yes, relieved.
I have a small question about the ADRC. You said it doesn't need the accurate analytical model of the disturbance.
Yes.
What is your opinion about its relation, I mean ADRC, to the fuzzy logic control? Fuzzy logic control has almost the same idea.
Yes, fuzzy logic controller have the same idea. We have done some comparison also with the fuzzy controller, Dr. Ahmed. And to tell you the truth, we published this also some time ago. And the performance of both of them were quite close, in fact. The performance of both of them were quite close. And there was no much drastic difference that we can say that one of them is better than the other. Because, as you mentioned, fuzzy control have the same advantage, in fact. We don't need a very detailed analytical model for the disturbance. Yeah, true.
Yes, okay. Thank you very much. Hope to see you soon, inshallah.
Inshallah, inshallah.
Thank you, Dr. Waleed.
Okay, thank you much for this. It was a pleasure. And I hope, inshallah, to see you all face to face. Dr. Jamil Abdu also, I heard about him, but I didn't meet him. So hopefully we can meet one day, inshallah.
Inshallah, we'll meet.
Dr. Waleed.